Hi, my name is Andrew McLaren. Today we're going to be talking about acid and base questions on the 2025 AP Chemistry exam. Now, these take on a couple different common formats. You're either going to be looking at the equivalence point, or maybe the half equivalence point, or maybe just initially when something is dissociating before you've added either the base that you're titrating with, or if you're sometimes you'll be titrating with an acid. Um, but typically, you're going to be seeing a titration curve of an acid with some sort of base being added to that. And as I've talked about in other videos before, the AP exam typically does not do one of these random points for having to do like one of those B, C, A tables or ice tables, but with like moles. Those can take a little bit longer. So typically they take these 3 points and ask simple questions about the general idea or like quicker calculations. So if we're looking at question 1 right here, it's basically asking you to think about what's happening at the equivalence point. And at that equivalence point, the amount of acid that you have present has given you a certain amount of moles of that acid. And then there's also some base that has been added with some volume of it to tell you how much of that base is present. And these two things should neutralize or cancel out. When you're at that equivalence point, this is when the acid is no longer buffering the solution and it's just basically been pulled forward all the way. And so in this case, we've got some sort of base, which is this NaOH, and we have that concentration right here. So we have the concentration of the base, and you can also see that it has a certain volume. So we have that volume as well. Then when we're at that equivalence point, we can go back and say, okay, that amount of moles of base cancels out this amount of moles of acid. So we can then go back and think about what's going on in terms of they're asking for this molar concentration of this initial solution. So that's this concentration that we're trying to solve for right here. And if we read the question, they've given us the initial volume of that as well. So we know this. We're trying to solve for that. And we also know this, and we know that. So this is a matter of just setting these two equal to each other and doing that math. So as we can see, we've got 0.0550 molar NaOH, and that is times its volume. So we've got, in this case, 16.0 milliliters of that base. And that is going to be equal to this concentration that we're trying to solve for of the acid times the volume of said acid, which was 10.0 milliliters. You could convert these into liters, these milliliters, but they're going to cancel out. So we can just simply solve for this. So if we just take our calculator and do that, it's pretty straightforward. And then we divide it by that 10. And we're getting this concentration of the acid initially to be 0.0880 molar of, I'm going to call it HA. So we're going to, instead of having this HASC, we're just going to simplify it down to HA, and then ASC minus will just be A minus. It's just the generic terms for an acid, so we're going to just work with that. We do have to just briefly think about sig figs. It looks like we had 3 sig figs there, 3 sig figs there, and 3 sig figs there. So this should be accurate to 3 sig figs as we've written it. So that's pretty good for this first part right here. So if you're at that equivalence point, it's a pretty straightforward calculation volume relationship. It's very, very quick to solve for relative to other things. Then they're asking for us to look at the pKa. Now this is related to our half equivalence point. There's a certain volume of base, and when you've got that volume of base, it ends up kind of canceling out. So there's this Henderson-Hasselbalch equation, which says the pH of a solution is equal to the pKa plus the log of A minus over HA. If the half of the HA has been turned into A minus, which is the half equivalence point, then you're just taking log of 1, which is 0. And so the pKa is equal to the pH when we do that. So it's a pretty easy thing to just look at this graph and be like, what is my pH when I'm at this like plateau? And it looks to me like our pH here is 4.0. So that is our pKa value. In other words, our Ka is equal to 10 up to the negative 4. So this is, although it's a weak acid, of the weak acids, this is fairly strong compared to some other values that you might get for an acid. So we've got these two parts kind of taken care of. And then this next question is, they've asked this a couple different ways before, but this is saying like if you're at a random point along this titration, it's about 4.7. So we're like kind of like here-ish for our pH. They're asking what's the balance between this A minus and HA. And you can do that by looking at your Henderson-Hasselbalch equation. If we think about this equation, they have basically given us the pH. We also know the pKa from that previous question, and so we should be able to solve for this ratio of A minus to HA. You can also see that we've gone past the half equivalence point, so most of HA has turned into A minus at this point. So it's mostly A minus. We can use that as a concept check in case you mess up this equation, because sometimes people will plug these two values in incorrectly or even write the formula with pH and pKa flipped. So if we have the pH of 4.7 and the pKa was 4.0, we can then relate that to this log. In other words, 0.7 is related to log of A minus over HA. And so we can take that 0.7 and we can say like that is, sometimes I have a hard time with converting between these two, but I'll ask myself like, okay, if I have log 2, or if I have 10 up to the second power and I log that, what is that? That's 2. So we're basically saying what is going on when you take 10 up to this 0.7 power. So you can think of 10 up to the 0.7 power is about 5. So our ratio of A minus over HA is about 5 to 1, or 5.0118. We could round that to the fact that this was 4.7. We could say that's 2 sig figs. So this is basically a 5.0 for that ratio between the two. And that is going to be a vast majority of the types of questions that you're going to see on the AP exam. I'm predicting that's going to be the case for 2026. If you watch the other videos, they tend to ask about equivalence point and half equivalence point calculations. We do have, on this exam, there's a few more places where you'll see acids and bases discussed. There's a couple problems where they're just using the term acid, but it's not relevant for the calculation. So like you can use this as like just a reaction and convert through that. So I'm not going to go over that in this video. Instead, we'll start looking further down, they do have another acid right here. This is asking more about like rate laws. So we're not going to worry too much about that in this video, though if you want, I might be able to do another video relating to that more specifically. And same sort of deal, this is actually forming an acid. It's not like an acid-base equilibrium either. It's more of a calorimetry problem. But when we get down here, they actually have in question 7 a couple places where they're discussing acids and bases. I'm going to actually start with 7a because it is relevant to the big picture stuff from that unit. So if we go down to 7a right here, this is something that acts as a base. So remember, a base could be something that can attach hydrogen onto it. So this might be then producing some OH minus if it was reacting with water. That's kind of the big picture. A base will produce OH minus or take in hydrogen. And so this has a couple places where hydrogen might attach. You might want to put that on this, but that's actually not a very good base. So there is some familiarity if you look at the carboxyl group right here, this carbon with these 2 oxygens. These are actually pretty good options to put hydrogen on there. There is some stability from this having resonance. So oftentimes if there's a hydrogen, there's some dissociation for a carboxyl group. But if we're talking about like an acid or a base property, if we're talking about like an alcohol, it's very, very bad at being an alcohol as well as very, very bad at being a base. Like it just can't really attach hydrogens very well or even give off their hydrogens very well. They're pretty stable groups. So if we look at the same sort of thing for carboxyl group, pK value, these tend to have carboxyl acids tend to have like a pKa of 4 or 5. So they're weak acids, but they're relatively pretty good at being an acid. Meaning also that like if we want to look at the pKb of the it's similarly like this is a weak base, but it's like okay at being a base. So this carboxyl group is actually a pretty good spot to put hydrogen on there. So either one of these would actually work out as places that can accept protons at a somewhat decent rate. You can also think of this as like positive and negative charges being attracted to each other. There's like a pretty negative zone around there, and so a hydrogen or a proton might be attracted to that. That's another way to think about this guy. Now, if we're talking about this equation right here, they're talking about its pKb expression. So if this is taking in that hydrogen, producing that hydroxide, the pKb expression is a good way of representing those products over those reactants, because this is just the product over reactant expression. And this is more closely related to just a dissociation if you look at part B. So part B right here is kind of like what we were talking about earlier for the acid-base expression. It's like right here at the very beginning of the titration. There hasn't been anything else added. They're not really being titrated. In this example, it's just a dissociation. So yes, this is an ice chart kind of thing, but it's actually not too bad. So they've given you the hydroxide concentration. They've also given you this 2.5 value. So if we were to take that reaction and do a little math, this is actually probably the easiest of the math things with those ice tables that you are used to doing. So we can see our ICE. This had a 2.5 molar concentration. Some of that dissociated, producing some of these things right here. hydroxide, a lot of times people write this as 0, but it really is like 10 up to the -7, but oftentimes the x kind of overshadows that, like how much this base is acting makes it so the amount of hydroxide already in the water is negligible. And you can actually consider this to be 0 because we're just starting off with that base that's going forward. So if we then think about this, we've got a 1.3 times 10 to the -5. So that is much, much bigger than 10 to the -7, which would be like 2 place values over. So that assumption of like just getting rid of that is fine. We can also see that this is quite a small value compared to that 2.5 right here. So it's fine to round this out as just 2.5 molar. And then you just kind of plug these into that Kb expression. So this Kb right here is like just a matter of plugging in what you're seeing. And that should allow you to solve for the Kb. So we've got that 1.3 times 10 to the -5. That's how much this kind of dissociate on its own, meaning that is the value for both these products that are formed in this reaction. And that is over this 2.5, or what is close enough to 2.5. So we can just round it to that. And you plug these in, and you can solve for your expression. And so if we do that, I'm just looking at this like 10 to the -10. Sounds like when you multiply these two things, they're going to make the product even smaller. So we can get just a good idea if our calculation is accurate just before we've even done any math. And use that estimation trick to kind of double check it. So we've got that 10 up to that -5. We've got that number right there. We can square that. And then we can divide that by 2.5. In other words, this is 6.76 times 10 to the -11 for our Kb value there. Meaning this is a pretty weak base. It's like not that good of a base, but it is going to act as a base to some extent, which was kind of what I was saying earlier. Like this is a weak base. I think the acid actually is its conjugate acid is a bit stronger than this being a base. So there's another expression here of Ka times Kb. Those will be equal to Kw. That's on your list of equations that they provide to you. But this is, if you were to look at K and Kb, a number of parts kind of cancel out to give you just the H plus and the OH minus multiplied by each other. In this context, though, we have 6 times 10 to the -11 as our Kb. That's this guy right here, what we found for earlier. And then Kw is going to be 1 times 10 to the -14. And then we can solve for Ka doing that with this divided by that. Now, my personal preference is to actually take the pKa's and the pKb's and solve for it that way. But you can take 10 up to that -14, and you can divide that by this guy, and you can get your answer. So if we take 10 up to the -14th power, hold on, the calculator's getting weird, 10 up to that -14th power divided by 6.76 times 10 up to the -11th power, we get a Ka value, which kind of sounds appropriate because -11, -14, this other number is kind of in that ballpark of -3. So yeah, 1.47 times 10 up to the negative, I think it was 4, negative 4. Which makes sense because 10 to the negative 11 times 10 to the negative 4 would get you 10 to the negative 15. But then you've got this 6.76 times the 1.47, which would take it up one place value. So that's totally appropriate. You can also, just a little bit of a hack, if you will, if you've got that that 6.076, if you just log that, you can, so if we got 7.76 times 10, sorry, this gets 7.76, yeah, times 10 up to the 11th, or negative 11th power. What you can do is you can log that. And so like the pKa plus the pKb adds up to like pKw, if you will. So like these two values add up to 14. And so we have like a 10.17 for this guy. And then you can, from that, solve for pKa and then do the log with that value. So you got 14 minus 10.17. And then you can say, okay, well, I've got 10 up to 3.83, but as a negative value. And yeah, that gives us the same thing that we found earlier. We do want to be careful with our sig figs. So for part 1, we had that accurate to, it looks like 2 sig figs. So this was 6.8 times 10 to the negative 11, that kb. And if we then use, you could either use that 6.8, and that's technically what you should be doing, but if you use the raw number here, they tend to be a bit more flexible with that particular rule with sig figs on the AP exam, just because sometimes it's asking multiple steps, sometimes it's just one step for similar problems. And then if we use that, the fact that it's 2 sig figs though, we do need to round this down to 2 sig figs as well, because that level of precision is important. So we've got 1.5 times 10 to negative 4 for that value there. So that's how I would work through those problems. The other parts right here are more related to mechanisms of reactions, so I'm not going to cover that in this video. But thank you for joining me. Let me know if you've got any other questions.